AVL trees in data structures, right. So, we have studied about binary search tree. Okay, we already know about binary search tree. It follows a property. What is the property? We studied about binary tree. On that, we know binary search tree has some additional properties. What is that property? Data on the left side of the root should be less than the root. Data on the right side of the root should be greater than root. Okay, that is the rule imposed on binary search tree compared to binary tree, right. One more condition, if we add on binary search tree, it becomes AVL tree. Okay, what is that condition, extra condition on this binary search tree? The height of its left subtree and right subtree should differ by at most 1. The height of left child, the left tree and the right tree should differ at most by 1. Okay, so before we go, let's study about balanced binary search trees. Okay, what is the rule here in binary search tree? See this example here, root is having 4, all the elements on the left hand side of the root are less than 4, all the elements here are greater than 4. Okay, this is the property of binary search tree, right. But if the difference between the heights of left tree and right tree, okay, if it is this is a full binary tree. If you remember, we studied about full binary trees, right. Full binary tree means you should have either 0 child or 2 child. Okay, so what is balanced binary search tree? In a binary search tree, if the height of the left and right, okay, if that is 0, if there is no difference in the heights of left subtree and right subtree, then we call it as full balanced binary search tree, like this example given here, right. So, binary tree, we imposed some restrictions and we made it binary search tree. On this, we are putting one more restriction there. Okay, what is that? The height of left subtree and right subtree should be 0. The difference between the height should be 0. Okay, then we call that as balanced binary search tree. Balanced binary search tree. Okay, same way, on the same binary search tree, if I put another restriction here, another constraint here, that the height of the left subtree and the height of the right subtree can differ by at most 1. So, there can be difference of 1, then such kind of trees are called as AVL trees. Okay, so let us go and study about AVL trees. So, here balanced binary search tree means the height of left and right will be 0. If k is 0, we call it as balanced binary search tree, or if at all we are talking about the balancing factor, then such trees are called height balanced trees. Such trees are called as height balanced trees. Let us see AVL trees. What is this AVL tree, right? So, here, right. So, this AVL stands for Adelson, Velsky and Landis. Okay, these are the 3 scientist names or the people who have introduced this tree. Only based on their first alphabets, this has been named as AVL tree. Otherwise, there is no naming convention for this. It is AVL tree, right. So, if that balancing, if the difference between the left height and left child and the right child, okay, or left tree and the right tree is 1, if it is 1, such kind of a tree is called an AVL tree. See here the example. See here one example, if you see 8. Okay, for this 8, what is the height of left tree? 1, 2, right, the height is 2. Here what is the height? 1, 2, 3, the height is 3. So, this is balanced. Okay, that root node 8 is satisfying the property that the difference is 1. So, this is perfect. This node is in proper structure of AVL tree. Now, go for the node 6. What is its height? This height is 1, this height is 0. On the left hand side, there is no child. Okay. So, the difference of 1 minus 0 is 1. So, this is also satisfied. We are saying that at most the difference could be 1, it should be 1. So, this is also satisfying the AVL tree property. What about this? Left is 0 and right is 0, difference is 0, this also satisfies. When we say at most 1, it can be 0 also. 0 and 1 are possible. Okay. So, this also satisfies the property. Next, come to 1, this node 1. Okay. So, left side it is 1 and 2, this is 2, and the right side it is 0. See, the difference between these two is 2, which is violating the rule of the AVL property, right. So, that is why this node 1 is not in proper structure. This is, so this node we have to convert this to a balanced tree, we have to make it balanced. Okay. Why this node? That is what AVL tree does not mean simply verifying at the root, comparing its left tree and right tree. You have to compare every node, that property is applicable for every node. Okay. So, this node 1 is not satisfying the property of AVL tree because its left is 2 and right is 0. So, the difference is 2, which is more than 1. What about this one? It is normal, it is satisfying because this is 1 and this is 0. What about this? Both zeros, satisfied. So, only this node is not satisfying the property of this AVL tree. See this one here, this case if you see 8, left and right is 2, left and maximum height, okay, maximum height, this is 2, satisfied. Then go for this 6, anyhow it is balanced, go for 1, it is balanced, 1 and 1 difference is 0. This tree is balanced now, right. So, AVL trees says that the difference of the maximum height of left tree and right tree should differ by at most 1, it can be 0 also, right. So, when can we say a binary tree is called an AVL tree? If it is a binary search tree, that is what we have been talking about, it should be basically a binary search tree, first property. Second, for any node x, for any given node x, the height of its left subtree and the right subtree should differ by at most 1. The difference between the left and the right should differ by 1. That is the important property here for AVL trees, right. So, this is not a AVL tree, this is an AVL tree, right. So, how do you find out the maximum minimum number of nodes in a AVL tree? Okay. So, the property is very simple here. Let us study about maximum number of nodes in a AVL tree. Okay. What could be the maximum number of nodes? Because we are restricting the height. Okay. So, if I take an example here, this way if I take, this could be one AVL tree. Why? Because the difference you see, level 1, level 2, level 3, right. So, there is one element here and the other element here. So, there is only difference of one extra level here, right. So, I was talking about, if I take example like this, this is an AVL tree. Why? Because everything is balanced here. This height is 3, for this root this is 2, the difference is 1, nicely satisfied. For this one, if you take this height is 2, this is 1, nicely satisfied. For this it is 1, it is 0, satisfied, 0, 0. So, everything is satisfied here, right. So, since what could be the minimum number of nodes in a AVL tree? Right, a full AVL tree if you take, a full binary search tree if you take, so this is a binary search tree, right. So, in this if you observe, what could be the minimum? So, if I take n is equal to here, how many levels are there? 4, if you take 4, right, or height is equal to 3. When you take height is 3, the minimum number of nodes will be 1, 2, 3, 4, 5, 6, 7, 8. Okay. Why? This is satisfying the property of AVL tree. What could be the maximum? Like this, putting this many elements there for n equal to 3. So, how many we are having? 1, 8, 9, 10, 11, 12, 13, 14, 15, right. So, 8 and 15 are the minimum number of nodes if the height of the tree is 3, right. Why? Because this is a balanced tree, even if I do not have this, this is also a balanced tree. Okay. Balanced in the sense, the difference of left and right is same, differ by 1, that is why we are saying. So, how do you find out that? Okay, let us see for this. So, let us assume the height of AVL tree is h and n of k indicates number of nodes in an AVL tree, right. When n is 3, we found out it is 8. Okay. So, if we fill the left subtree with height h minus 1, then we should fill the right subtree with height h minus 2, right. See, this left subtree I have filled with height how much? The total height of this tree h is 3, h minus 1 means 2. See, the height of this tree is 2, whereas the height of this tree is 1. That is it, no? For this right child, for the circled one, the height is 1, right? So, if you are filling a left subtree with h minus 1, then definitely the right right subtree should differ, the height should be h minus 2, like this. Okay. As a result, the total number of nodes or the minimum number of nodes in a AVL tree can be given by n of h equal to n of h minus 1 plus n of h minus 2 plus 1. Okay. N of h minus 1 plus n of h minus 2 plus 1, meaning number of nodes in the left subtree with height h minus 1, number of nodes on the right subtree with height h minus 2 plus 1. Why plus 1? That is the root. For root I have to count, right? Okay. So, this is the equation for that. Now, if you see where n of h minus 1 indicates minimum number of nodes of height h minus 1. So, I need not have this also, but this is not balanced. So, definitely I should have it. Okay. Next, n of h minus 2, minimum number of nodes with height h minus 2, this case. Okay. So, I can even remove this. Why? This is balanced 1 and 0, right. So, it is 7, not 8. Okay, right. So, from and 1 indicates the current node, that is the root. Okay. So, this way you can find out the minimum number of nodes in a AVL tree, right. How are you finding it? The number of minimum number of nodes of height h minus 1 and minimum number of nodes on right side h minus 2, right, and plus the root. So, this gives us the minimum number of nodes in a AVL tree. Okay. Let us see something here. So, if you give height n of h minus 1 to both right and left, meaning if you make it a balance like this, something like this you gave, this is balance, no? Left side is 2, right side is 2, difference is 0, left side is 1, right side is 0, difference is 1, this is 1, this is 0, difference is 1, difference should be 1, do not take plus or minus here, right, and the others are also satisfied. Okay. So, when you give both h minus 1, so if you solve this recurrence relation, you get it is something as the height of an AVL tree. Okay. To find out the minimum height of an AVL tree, that is given by order of log n, where n indicates the height of the tree. So, if someone says that given a height of a tree is 3, find out the minimum number of nodes in AVL tree, answer is log 3. Okay. Log 3 value if you calculate, again for small numbers it may differ, but if you take some 30, log 30 you get some appropriate value. Maybe because log 3 value is small, you may get near to that. So, it can be 2 or it can be 3 also. Okay. So, it may little differ, but for large numbers it will satisfy it. Okay. So, the height of a AVL tree, given the height of an AVL tree, the minimum number of nodes in an AVL tree is order of log n, that is log n number of nodes in the AVL tree. Okay. So, this is the equation. We will solve some problems, numerical problems, and see after understanding few concepts in AVL tree, we will try to solve some numerical problems. Given height equal to 3, what is the minimum number of nodes, what is maximum number of nodes, right. All these problems we will try to solve it. Tree declaration, how do you declare an AVL tree, right. So, this is important. See, we know binary search tree is also a double linked list. Why it is double linked list? Because we are maintaining a left pointer and a right pointer with the data value here, right. Along with this, we are going to have an extra parameter in that node structure, that is height. Okay. We are going to have an extra parameter, that is height. So, your node structure is going to look something like this. I will have a node where I will have a left pointer, I will have the data, I will have the height, and I will have the right pointer and the left pointer. Okay. So, this will point again to another node of 4 size like this. This will also point to another node of 4 size. Okay. We are maintaining height of every node in the node itself. Okay. In every element we are going to store the height of also. So, whenever this height is not proper, you have to balance the tree, you have to do some operations to balance the tree. Okay. So, this is just a declaration of tree, AVL tree. We are including along with the data left and right pointers, we are going to have a height variable also h, right. Why we need h? Because our problem itself says that AVL tree concept itself says that the tree should be height balanced, meaning the height of left subtree and the right subtree should differ by at most 1. Okay. So, this will help us, this H will give us the difference between the both the trees. So, for this node, meaning if I draw a structure like this, so for this node H value will be 1. Why? The difference between left and right is 1. So, it is an order. Okay, it is in order. Now, when I say that some trees, if they are not in order, if they are not in AVL tree order, we have to do some balancing, we have to do some operations. Okay. For example, take like this, you have a tree something like this. Okay. This node is balanced. Why is it balanced? This height is 1, this is 1, 2, 3, this is not balanced. So, definitely in this case here, here the H value will be 2. Why? The left and right difference is 2. Okay. Here this is balanced, so height will be 0, H value will be 0. Here the H value will be 2 minus 0, 2. Here H value is 1, here H value is 0. So, in the node itself, if you are maintaining the H value, the height value or the difference, whatever it is our implementation, if you are storing the difference of the left and right tree in that particular node, this will tell us to identify which node is not balanced. Okay, which node is to be balanced. If you go back to see this example, if you see, right, this is 10 and 11. We found out that this is balanced because H is equal to here 1, here H is equal to 1, here H is 0. That H value, which is the difference, here H value is 2, here it is 1, here it is 0. So, among all the nodes, which node is having the height value or the difference of height more than 1? This node. Only that I have to balance, I have to do some adjusting there. Okay, such that that node or that tree becomes balanced tree or that tree becomes a AVL tree. For that reason, we are maintaining a new variable called height. Okay, this is normal, left data, right is normal, we are having height here, right. How do you find out height of an AVL tree? Simple logic, just ask the root, root will give you the height. Okay, if you want to know the height of a tree for this tree, I am maintaining no H is equal to 1, H is equal to here, I am maintaining all those values, right. So, if you want to know the height, it directly it will give the root of height. Okay, root of height will tell us the height of the tree. So, we are going to maintain the maximum height here, we are going to maintain the maximum height. So, this is 2 and this is 3. So, 3 will be there here. One implementation, in some placement questions they have asked us to maintain the difference of the heights in that value, so that it is easy for us to find out which node is not balanced. Okay, but for here this logic it tells us just take the root as input, if it is null give -1, otherwise simply give root of height. So, the root is maintaining 4 things, right, in that one is data, other is the height, thus you return, that is it, very simple to find out the height of a tree. Okay. So, this is about the little introduction about AVL trees. If you quickly summarize, we have studied about binary search trees. In that we are having another kind of binary search tree called balanced binary search tree, where the height of the maximum height of the left subtree and the maximum height of the right subtree differ by 0. Such trees are called as balanced binary search tree. But if that difference between the left tree and the right tree becomes 1, at most 1, those kind of trees are called as AVL trees. Okay. The property is it should be a binary search tree and the difference is at most 1, right. So, we have seen how do you find out the maximum and minimum number of nodes in an AVL tree. Okay. So, we have studied that the left tree and the right tree should differ by 1 to become an AVL tree, right. So, this is the declaration of AVL tree along with the data left and right pointers in the single linked list format. We are also going to store a height value which will maintain the height of the tree of every node, meaning if I have something like this, here I will maintain the height, here also I will maintain the height of this tree will be here, height of this tree will be at this node. Like this we are going to store height at every node. Okay. So, this is a simple logic to find out the height, it is very simple. If you are giving root as the input, it will give root height as the output, but that value directly printing the value of a node. right. So, this is about AVL tree, but there is one problem in AVL trees. What is that? Suppose if there is a tree like this, okay, how do you convert this to AVL tree? Okay, or when can the challenges, when can a tree violate the properties of AVL tree? Okay, so suppose I have a tree like this. See this example here. Suppose I am having a tree like this example here. If I insert another element here, right, so this height becomes 3, this height is 2, it is still balanced. But if I insert a node here and then another node here, is this balanced one? No. It means a tree is becoming unbalanced. A tree is becoming unbalanced either because of addition of some number or because of deletion of some number. Okay, either because of insertion or because of deletion, right. So, what kind of violations can happen, what reasons can cause a tree to not to become an AVL tree, right, that we have to study, we will see that.